Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 5, Section 2, Chapter 3, Topic 2.
Semiconductor packaging assembly is a meticulous process that involves a series of well-defined steps to transform individual semiconductor dies into fully functional packaged integrated circuits, ICs. These steps, collectively known as the assembly flow, encompass die preparation, die bonding, wire bonding or flip chip bonding, encapsulation, testing, marking, and packaging. In this comprehensive overview, we will delve into each of these flow steps, elucidating the procedures, techniques, and considerations involved in semiconductor packaging assembly. Die preparation. The assembly flow typically commences with die preparation, where individual semiconductor dies are fabricated and prepared for assembly. This involves dicing silicon wafers into individual dies using precision cutting tools, followed by cleaning, inspection, and sorting to ensure uniformity and quality. Die preparation is crucial to ensure that each die meets the specified dimensions, electrical characteristics, and reliability requirements. Die bonding. Once the dies are prepared, the next step in the assembly flow is die bonding, where the semiconductor dies are attached or bonded to carrier substrates or lead frames. Die bonding techniques vary depending on the package type and design requirements. Common methods include epoxy or adhesive bonding for surface-mounted packages and soldering for through-hole or flip-chip packages. Die bonding requires precise alignment and placement to ensure proper electrical connections and thermal dissipation.
Interconnection formation.
Following die bonding, interconnections are formed to establish electrical pathways between the die and the external leads or contacts of the package. Wire bonding is a widely used technique for creating these interconnections in traditional packages, where fine wires made of gold, aluminum, or copper are bonded from the die pads to the package leads using ultrasonic or thermocompression bonding. In flip-chip packages, solder bumps or conductive bumps are used to create direct connections between the die and the substrate. Encapsulation. After interconnection formation, the semiconductor package undergoes encapsulation, where it is sealed and protected using materials such as epoxy resin or molding compound. Encapsulation provides mechanical support, environmental protection, and structural integrity to the packaged ICs, shielding them from moisture, dust, mechanical stress, and other external factors. Encapsulation may involve transfer molding, compression molding, or other molding techniques depending on the package type and production requirements.
Thermal management.
Thermal management is a critical aspect of semiconductor packaging assembly, particularly for packages with high power dissipation requirements. Heat sinks, thermal pads, thermal vias, and other thermal management elements may be integrated into the package design to facilitate heat dissipation and regulate operating temperatures. These elements help prevent overheating and ensure optimal performance and reliability of the packaged ICs. Testing and quality assurance. Throughout the assembly flow, packaged ICs undergo rigorous testing and quality assurance measures to verify their functionality, performance, and reliability. This includes initial testing to detect defects, functional testing to assess product features, and final inspection to ensure adherence to specifications and standards.
Testing and quality assurance procedures may vary depending on the package type and the complexity of the integrated circuits. Marking and packaging. Once tested and inspected, the packaged ICs are marked with serial numbers, date codes, or other identifying information using laser marking techniques. They are then packaged into trays, tubes, or reels for shipment to customers. The marking and packaging process may vary based on the package type, customer requirements, and industry standards. Future trends and innovations. As semiconductor packaging technology continues to advance, new trends and innovations are emerging to enhance the efficiency, reliability, and performance of packaged ICs. This includes the adoption of advanced materials, manufacturing processes, and design techniques to improve thermal management, reduce form factor, increase functionality, and meet the evolving demands of the electronics industry.
In conclusion, the assembly flow of semiconductor packaging involves a series of well-defined steps aimed at transforming individual semiconductor dies into fully functional packaged ICs. By understanding the procedures, techniques, and considerations involved in each flow step, manufacturers can ensure the quality, reliability, and performance of packaged ICs, driving innovation and advancement in the electronics industry. Thanks for watching.
Please like, share, and subscribe.